Hello, I'm Ty. I'm from University of California, San Diego. I'm excited to present our work on Hamiltonian-based neural ODE networks on the SE3 manifold for dynamics learning and control. First, let's talk about dynamics learning. Accurate robot dynamics is important for motion planning and optimal control. It's defined as a function f of the robot state xt and the control ut that governs the time evolution of the state. The question we care about in dynamics learning is how to learn the dynamics from data. To answer this question, we want to find approximated dynamics f hat with parameter theta that minimizes the loss function with the training data from the true dynamics. The first approach for this problem is white box system identification, which requires domain expertise and might have many assumptions on the system. Meanwhile, the black box model, like neural networks, is flexible but requires a huge amount of data. To improve on this, the gray box approach imposes some prior knowledge, like physics law, to design the model. Our paper belongs to the gray box category that imposes the law of energy conservation by using Hamiltonian dynamics. However, compared to the previous Hamiltonian-based works, we consider the robot state on the SE3 manifold instead of Rn. The SE3 manifold is very common for mobile robots, where the robot state includes the position S, the rotation matrix R, the linear and angular velocity v and omega. The state has to satisfy the SE3 constraints shown in red here. It turns out that if we reformulate the states x as coordinates q and twist c, the Hamiltonian dynamics over the SE3 is governed by this Hamilton's equation with three unknowns: the mass m, the potential energy v, and the input coefficient g. We are going to use this Hamiltonian formulation to design our model. Our dynamics learning approach is to place the approximated function f hat in a neural ODE framework, and then we can roll out the state trajectory using an ODE solver. The gradient of the loss function is then backpropagated using an efficient adjoint method. Now the idea is to use three neural networks for three unknown m, v, and g, and then we're going to impose the Hamilton's equations on the architecture of f hat. By construction, we guarantee energy conservation and the SE3 constraints. Now given a learned dynamics f hat, we design a controller for trajectory tracking problem. So basically, we want to find a control policy pi so that the robot can track the desired state trajectory x star starting from x naught. The main idea is that without any control, the learned dynamics does not have the desired state as an equilibrium. So we need to add energy through the control u to achieve a desired total energy that has an equilibrium at the desired state. To find the control, we just need to match the two Hamilton's equation and solve for u. We then apply our energy-based controller to both fully actuated systems like pendulum and rigid body, and under-actuated systems like QUADROTOR. For experiment, we first test our learning approach with the pendulum with these graph truth values. Our learning method can learn the correct mass, the correct input coefficient g, and the correct shape of the potential energy v. We verify the energy conservation by showing that the total energy of the system is a constant when the control is 0. The SE3 constraints are also satisfied by our framework. This is a demo of our energy-based controller smoothly drive the pendulum to the upright position. Next, we validate our approach with an under-actuated quadrotor with 1D thrust and 3D torque. We use a drone simulator and collect data from 18 flights. The results show that we are able to learn the right mass, the right input coefficient, and the gravitational potential energy. We also verify that the energy conservation and the SE3 constraint are satisfied by our framework. Finally, we test our energy-based controller with a diamond-shaped trajectory. We can see that the drone is able to track the desired trajectory using a dynamics learned from data. In conclusion, we propose a dynamics learning model that respects the energy conservation and SE3 constraints. We design a unified energy-based controller for trajectory tracking. For future work, we'd like to explore multi-rigid body systems like robot arms and investigate online learning and adaptive control. Thank you for your attention. We invite you to visit our project website and check out the paper and the code.